Welcome back. Today we're doing section 7.3 on local maxima and minima in multivariables. So we have two main theorems that we're going to put to work for this. This is not a more heavily proof-based course, so we're just going to state the theorems. So theorem number 1 says that we have a function f at some point AB here are constants, is an extremum. In other words, a max or a min of f a couple things need to be true. F of x and f of y have to exist. These are, remember, partial derivatives. Partial with respect to x, partial with respect to y exist at point AB. And f sub x of AB is 0. F sub y of AB also 0. So we do have to meet those conditions. So we can use that to some proofs. Lost my page here. Shaking you there. There we go. Oop. All right. So we're going to use theorem 1 to show. Sometimes they'll say prove, sometimes they'll say show. They're implying the same idea. There are no local extrema or f of xy is 24 minus 4x minus 7y plus 2y squared. So this is some three-dimensional surface, basically. If it were just a y and an x, no f involved, we would be in the xy plane. Throwing the third variable in, we have the plane, and we can come out from the plane or back further in three-dimensional now. And with theorem 1, we can prove that this one will not have a highest or lowest point. So we need to find partial derivatives. So partial with respect to x, 24 is a constant, negative 4x, derivative would be negative 4. The minus 7y is treated as if it's a constant since x is our independent variable at the moment. Same thing with the 2y squared. Partial with respect to y of xy. Derivative of a constant is always 0. Second term now becomes a constant, also 0. So we have negative 7 plus 4y. So we have an extremum if there's some point AB such that the partial derivatives are both 0. Well, we can definitely find a y value where the partial is 0, but if we look at the partial with respect to x, 0 is never going to equal negative 4. Therefore, there is no local extremum. Okay, so our next theorem is a little bit longer, but it's really a little bit of just a sort of plug and play kind of thing. You're not going to be expected to memorize the 4 cases that are covered in this theorem, just be able to put them to work. So theorem 2. Z is going to be our f of xy, so two independent input variables. We're going to assume that we meet the criteria from theorem 1. F sub x of xy is 0. F sub y of xy also 0 at point A, B. We also need to make some other assumptions. The second derivative exists centered on AB. One thing that's a little bit different in three-dimensional work versus two-dimensional work, when we were doing our derivatives, when we had just one independent variable, we were usually assuming that the derivative existed on some open interval on the usually x-axis around AB. Well, now that we have 3 dimensions, basically we're going to put a little circle around point AB instead of surrounding it in a linear fashion on just one axis. Now we're going circular. Okay, some definitions as well. Cap A is going to be f sub xx of AB. Cap B, f sub xy of AB. Cap C, f sub yy of AB. So once we have those 3 values in hand, there's going to be 4 cases. Again, you don't need to memorize the 4 cases. They're going to be provided for you. Case number 1, AC minus B squared is greater than 0, and A is less than 0, then f of AB is a local max. Case 2, AC minus B squared greater than 0, and A is also greater than 0. We have a local min. Case 3, AC minus B squared less than 0. We have what's called a saddle point. If you've ever eaten a Pringle potato chip, those are in the shape of saddles. They have a saddle point on those. Basically, in one direction it's curving down, the other direction it's curving up. So it's not a min, not a max, but a max from one direction, a min from the other saddle point. In case 4, you probably already expect what's coming. We had greater than 0, less than 0. The last possibility is equal to 0. Test is inconclusive. So it doesn't prove that it is not an extrema and not a saddle point. The test just isn't able to be used, and you have to use a different test that is not something we go into in this course. Okay, so we will just put that to work. So f of xy, x squared minus 4xy plus 2y minus 6. And we're going to find our local extrema using theorem 2. So I need all of my partial derivatives. So I'll start with partial with respect to x. So that would be 2x minus 4y. So remember, y at the moment is being treated like a constant, just like the 4 was. Derivative of an x to the first would be a 1. Y is a constant at the moment, so this derivative is 0, that derivative is 0. Partial with respect to y. X squared would have a derivative then of 0, since y is now my independent variable. The negative 4 and the x are constants. Y is a variable at the moment, so negative 4x would be my derivative. And finally, my derivative of 2y is 2. So we're looking for places where these are both 0. We can just sort of make a little mini system of equations out of this. You remember those from your Math 95 days or your equivalent that you took somewhere else. So 2x minus 4y is 0, together with negative 4x is negative 2. And we're just solving that system. This one, just substitution, elimination, graphing, any of them would be fairly straightforward to do. We'll just do elimination. So multiply both sides of row 1 by 2, and we have 4x minus 8y is worth 0, together with 4x is equal to negative 2. Sorry, negative 4x equals negative 2. So negative 8y is worth negative 2, so y is positive 1/4, and then we can find our x with that. So 2x minus 4 times 1/4 is 0, so 2x minus 1 is 0, so x is half. So our AB here is 1/2, 1/4. That's the place we're interested in. So now we need our second derivatives. I'll scooch this on over. Okay, so our A value f sub x, derivative of this with respect to x would just be the 2. F sub xy, either differentiating this one with respect to y, I would get a negative 4. Notice differentiating this one with respect to x, I would also get the negative 4. And finally, f sub yy would be a 0. So f sub x at 1/2, 1/4 is 2. F sub xy at 1/2, 1/4 is negative 4. And f sub yy of 1/2, 1/4 is 0. Occasionally the variables won't drop out and you'll have to plug in a value. So we have our A, B, and C. And here's our C.
Go for a walk.
Okay. So our AC minus B squared for this one. So A times C, so that would be 2 times 0 minus negative 4 squared. So AC minus B squared lands us at negative 16. That is less than 0. So AC minus B squared less than 0. We are looking at a saddle point. Okay, so next one, again, we're going to put theorem 2 to work for us still. This time f of xy is going to be x natural log of y minus y plus 2. So again, we'll start with our first partial derivatives. Natural log of y at the moment is a constant. Derivative of x is 1. So 1 times natural log of y is natural log of y. No x's in the next two terms, so those drop out. Partial with respect to y of xy. Now the x is just a constant. Derivative of natural log of y, of course, 1 over y. And derivative of negative 1y is negative 1. Derivative of plus 2 is always a 0. If you'd like, you can also clean that up, xy minus 1. So again, we make a little system out of these. We want these to be worth 0. So natural log of y, we want to be equal to 0. We also want x over y minus 1 to equal 0. While solving that first equation, notice this one is a nonlinear system. We can go from logarithmic notation over to exponential notation. Natural log base is implied to be an e. So e to the 0 is worth y, which tells me y is 1. Any non-zero number to the 0 power is 1. That allows me to find my x in the second equation. X divided by 1 minus 1 is 0. So x is equal to 1. So now we're interested in the point 1, 1. So then we move on to our second derivatives. F sub x, x of xy. So derivative of natural log of y, treating x as the variable, 0. No x's were involved in it. F sub xy of xy. Differentiate this guy with respect to y, we get 1 over y. Differentiate this guy with respect to x, we also get 1 over y. Since the y down here would act like a coefficient, and we have the implied factor of 1 out front. And finally, f sub y of xy. Let's see, we'll do a little work to this guy to make him a little easier to work with. Xy to the negative first minus 1. So that would be negative 1 x, y to the negative second. Or opposite of x over y squared. So we have our second order partial derivatives. Now we're ready to find a, b, and c. A and b are nice pretty constants. I'm sorry, no, that is a y, not a 4. A is a constant. So f sub x of 1, 1. It was a constant before I even plugged in the 1, 1. It was already a 0. That's our A. F sub xy at 1, 1 is 1 over 1, which is 1. There's our B. And f sub y at 1, 1. Negative 1 over 1 squared, negative 1. That is our C. Okay, so then we will look at our values of, for starters, AC minus B squared. So 0 times negative 1 minus B squared. B squared here is 1 squared. Negative 1, so that is less than 0. So we have another saddle point. If we had a positive, then we just have to check to see is A positive or is A negative. Okay, So it is possible to have multiple extrema as well. F of xy. For the next one, x to the fourth plus y to the fourth minus 4xy. Partial with respect to x. 4x cubed. Middle drops out. Minus 4y. Partial with respect to y. First one drops out. Second one, 4y cubed. Third one, negative 4x. I'm going to set those to 0 and solve the system. This one, again, a nonlinear system. So substitution is probably the easiest way to go. Both of those we can sort of factor divide both sides by 4. Make them a little smaller. So x cubed is equal to y, and y cubed is equal to x. And we'll just do a little substitution. So y is the same as x cubed. So plugging 1 into 2, we have the y is the same as x cubed. So x cubed is equal to x. Power to a power, we multiply. X to the 9th minus x is 0. X by x to the 8th minus 1 is 0. And then just a little factoring. Okay, first one, x equals 0. The next two would give us non-real solutions. If we're looking for maxes and mins, whether it's in 2 dimensions or 3, we're still looking to stay in the real numbers. So we'll toss those two guys out, but x could be a -1, or x could be a 1. So we have 3 values of x, which will also give us then 3 y values. So if x is 0, y is 0. If x is -1, y is also -1. And if x is a positive 1, 1 cubed is still 1. So we still want to find our second derivatives. So f sub xx, differentiating this guy again with respect to x would be a 12x squared. Next term would drop. F sub xy, should leave my of xy in there. This guy with respect to y would be a -4. This guy with respect to x also a -4. And that one is actually a -4. And finally f sub yy of xy. This guy with respect to y again, 12y squared. So then we find our a, b, and c for all 3 of the points, 0, 0, 1, 1, -1, -1. So looking at the 0, 0, f sub xx of 0, 0 is 12 times 0 squared, which is 0. That's our a for this point. F sub xy of -1, of 0, 0. Let's do 1 point at a time. That's worth a -4. That's our b. And finally, f sub yy at 0, 0. 12 times 0 squared is still 0. That's our c. So then we want ac minus b squared for this point. So a times c is 0 times 0 minus b squared, -4 quantity squared. 1, 2, 3 negatives is a negative. Less than 0, so 0, 0 is the saddle point. Then we'll try out the -1, -1. So f sub x of -1, -1. 12 times -1 squared is still 12. That's our alpha. F sub xy of -1, -1 is -4 no matter what. That's our Bravo. And our Charlie, f sub yy of -1, -1. 12 times -1 squared, even number of negatives kicks it over to a positive. That's our Charlie. So AC minus B squared. So 12 by 12 minus -4 squared. So we have 144 minus 16. Definitely greater than 0. So AC minus B squared was greater than 0. If it's greater than 0, then we also have to find what A is. So our A value, remember, was equal to a positive 12, which is greater than 0. So using theorem 2, which again you don't have to memorize, just flip back to it. I'll be providing it for you. We know that this then is a local minimum. And finally, our 1, 1. F sub x of 1, 1. 12 times 1 squared is 12. That's our A. F sub xy at 1, 1 is a -4. And f sub yy at 1, 1. 12 times 1 squared is still 12. That's our C. So AC minus B squared for this guy is the same value of 128. 12 by 12 minus -4 quantity squared. 128, which is greater than 0. A for this one, also greater than 0. So this is another local min. All right, so after this, we're going to do a couple of word problems. I think I'll sort of split the section. So I'll give you the full assignment now, and in the next video, I'll ask you to complete the couple of word problems that we have as well. So this is section 7.3, part 1. Skip word problems for now. So if you're in the old book, try out 9 to 29 odd, 39, 43, and 45. Again, hold off on the word problems that are mixed in there. The new book, 9 to 33 odd, 43, 47, and 49. If you have any questions, please feel free to get in touch with me. Otherwise, stay safe out there, and I'll see you for part 2 next time.